Okay, before I do some examples, we should determine if we're going to use Sn1 or Sn2. So, will Sn1 occur on a methyl carbon? No. And why is that? Well, remember in Sn1, our leaving group leaves first, and then we have that carbocation. And we need our carbocation to have alkyl groups to stabilize it. So this carbon won't have any alkyl groups. There will be another carbons connected to it, like a secondary would or a tertiary, to stabilize that carbocation. So Sn1 will not occur on a methyl. What about Sn2 methyl? Yes. Why is that? Well, Sn2 is a concerted reaction where the nucleophile is attacking that carbon and that leaving group is leaving at the same time. And Sn2 is governed by sterics. So like on a tertiary carbon that has too many sterics, so it can't attack. So I can just say it won't happen on a tertiary because a tertiary carbon will be too sterically hindered for a, so let's say our leaving group's right there. We won't be able to attack on this carbon because there's too many things in the way. Well, a CH3, there's nothing in the way, so it can attack just fine. Since I jumped down here, let's just look at the tertiary Sn1. Will that occur? Yes. And the reason why is because that carbocation, because in Sn1 our leaving group leaves first, so a carbocation with some carbons attached to it will stabilize this positive charge by hyperconjugation. So that will stabilize that carbocation by hyperconjugation. Let's look at primary. Will primary occur on Sn1? No, because once again, that carbocation will not be stabilized by only one other carbon. What about Sn2? Yes, because it won't have a problem attacking backside on a primary carbon. There will be nothing in its way, just another carbon, which is not a problem. So a CH3 would occur faster than a primary, but they're both really fast. This is the whole point of this chart. Secondary or secondary? Will secondary occur for Sn1? Yes. Will secondary occur for Sn2? Yes. But how do we determine which one's which? Well, for Sn1, you look for a polar protic solvent, such as H2O. So that's pretty much all you really look for. It's like a weak nucleophile as well. So weak nucleophile. That's what you're mainly looking for if it's Sn1 or Sn2. If we're in a polar protic solvent such as H2O or methanol, so CH3, OH, or we have a weak nucleophile, or both I should say, we will do a secondary, on a secondary carbon we'll be doing Sn1. So about Sn2, well, we're looking for a polar aprotic solvent. So what's a polar aprotic solvent? That would be something like THF. I don't know what that is. It's like tetrahydrofuran. I believe it looks something like that, with an oxygen with this like 1, 2, 3, 4, like 4-membered ring with carbons, but there's a total of 5. So let me make this a little bit bigger, like this. THF, tetrahydrofuran. I probably am pronouncing that wrong, but that's what you're looking for. THF and a strong nucleophile, such as sodium hydroxide. Now, since we have this idea of what we should be looking for, this is all really easy. No, yes, no, yes, yes, no. But right here is where we run into some trouble. So Sn1, we want a polar protic solvent with a weak nucleophile. And for Sn2, we want a polar aprotic solvent like THF. Or we want just a strong nucleophile. So that's going to be Sn2. Now let's do some examples. Okay, let's do some examples. But first, it appears that I missed this guy right here. I forgot the reaction arrow. Reacting that with sodium cyanide and acetone. Okay, let's go to this first problem right here, number 1. So this carbon right here is connected to 1, 2, 3 other carbons. So this electrophilic carbon right here is tertiary. And our nucleophile is methanol, which is weak, which will also indicate we are doing Sn1. Because on a tertiary carbon, we do Sn1 reactions. We do not do Sn2. So the first thing that happens in Sn1 is that our leaving group leaves. So we'll get something that looks like this, where our hexane ring has this positive cation charge, and this substituent right here is this guy right here, where we have 1, 2, 3 carbons, 1, 2, 3. Thing about Sn1, we can attack from the top and the bottom, so we're going to get a racemic mixture, or so it might look. So I'm going to draw our racemic mixture real quick. Our oxygen is what's doing the attacking because it has that lone pair, so it's going to come in and attack. Not that one, because our leaving group leaves first. It's going to attack the cation, the carbocation. And our oxygen is bound to an H and a CH3. Now this gives a positive charge on our oxygen. Another molecule of methanol in solution will come up. So this is just another molecule of methanol. Will come up and attack that proton and shift those electrons back onto the oxygen. So we'll get something that actually looks more like this, where that hydrogen or that proton is gone and we have our methyl group. So that's what our molecule would look like. We cannot forget our other substituent. So that's our first one. We can also attack from the other side. So we'll have another molecule that looks like this, where the nucleophile is not wedged but is rather dashed, because we are attacking from both sides. That's characteristic of Sn1. And this guy is wedged. But what I was trying to hint at is, it turns out this reaction doesn't give us a racemic mixture because these two are actually the same molecule. Because if I rotate this or flip this, this guy will become dashed, which it is right here, and this guy will become wedged, which it is right here. So these are actually the same molecule. So that'd be a trick question on your test. If they ask you, give us the major product, you should not draw both of these because your professor will mark it as wrong, because these are the same thing. We only have one molecule formed because these two are the same. So let's move on to our second example. We have a carbon bound to 2 other carbons, so that's secondary. Our nucleophile is strong because we can get rid of the sodium cation and just write it as OCH3. And this has our minus charge. If you do the formal charge, we'll find out that has a -1 because 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1. You guys should know how to do formal charges. So this is going to be an Sn2. Remember that I said on a secondary carbon, we can either do Sn1 or Sn2, but since our nucleophile is strong, we're going to do an Sn2 reaction. So an Sn2 reaction is concerted. So we are going to do a backside attack, and the leaving group is going to leave at the same time. So we'll get something that looks like this, where our OCH3 becomes dashed because we did a backside attack. So since this is wedged, this will make a dashed bond. If this was dashed, this would make a wedged bond. So I hope that makes sense. So let's go to this last problem. I overemphasize this wedged methyl group right here for a reason. So first, let's do the problem. This carbon is bound to only one other carbon, so we have a primary carbon. So what is that, Sn1 or Sn2? Well, Sn1 can't happen because we need hyperconjugation to stabilize that carbocation. So we are going to do an Sn2 type reaction. So once again, get rid of the sodium cation and just draw Cn as its anion. We're going to do an attack right here on our electrophile, and our leaving group is going to leave at the same time. Now, Is this guy going to become wedged or dashed? You may think dashed, but it doesn't. It actually stays wedged. And the reason that happens is because we are not doing any type of attack on this carbon. It's going to stay the same. If we were doing an attack on that carbon, yeah, we would have an inversion of configuration. So like we did here, if this had like our leaving group, we did an inversion of configuration. But we are doing nothing with this carbon, nothing at all. So we're leaving that the same. So this would be your answer for these types of problems. I hope this video helped you. If you have any questions, please feel free to leave a comment down below. Please give this video a thumbs up and subscribe. Thanks for watching.